computation of homology groups. This is example 1. Consider the simplicial complex. Let's take a very simple one that only has a zero simplex. Then the only chain complex we can construct out of this simplicial complex is the zero chain, right? So the zero chain, which we denote with C0 of k, is nothing but some a p0 where a belongs to integers. And since this a belongs to integers, you can think of that this chain group is just the group Z itself. Why? Because you can think of this A as some sort of a basis. Okay, it will be more clear when we see some other examples. And for now, since there is only one zero simplex in the simplicial complex, and the only chain complex that we can construct is just a zero chain, and this is isomorphic to the group Z. Okay, and you can even show that just by taking this element over here where my cursor is hovering. You can take this, and since A belongs to Z and the simplicial complex, the zero complex or the point is just there, you can see that all the group axioms are satisfied. So this itself forms a group, as we discussed earlier. Okay, so now since we only have one element over here, we say that the only cycle is a zero cycle, which is just our P0. So the only cycle here is just P0. Okay, we have C0 of k is equals to Z0 of k. Why? Because we just have only one cycle, and we can again use some a prime where a prime belongs to Z to create all the cycles, right? Arbitrary cycles. For different a prime, it will give us some different cycles, but the main point is that it has this P0, the zero simplex or the point. So that's why we say that this C0 and Z0, they are equal to each other. So we are done finding our C0 and Z0, and since the elements of our cycles will generally assume this form, if I want to compute the boundary elements, the elements of the boundary set, then I can easily see that no matter which element I take, and then I act the boundary operator del1 on some a P0, because we want to find the zeroth homology group, right? Since we can only construct the zero chains, we want to find H0, and to do that we also need to find P0 and Z0. But the elements of B0 or the zero boundary will come from this thing, right? And this is just 0. Why? Because by definition del1 P0 is 0. A point doesn't have a boundary. So you can see that there is only one element in B0, and that is just the 0, or so to say the identity element of Z under addition. So this B0 of k is just written like this. Now we have all the essential informations to compute the zeroth homology group. So this is just z0 of k by p0 of k, which is equals to, since z0 and c0 they are both the same thing, I write this as c0 and this as the identity element. Please do not confuse this with dividing with 0. Rather, you should always consider whenever you see a 0, you can think of it as an identity element. Okay. And c0 is what? C0 is isomorphic to z, the group of integers, right? And your quotient, you are quotienting, or you are modding that with the identity element. So this is just the group of integers. So your h0 of k is essentially isomorphic to the group of integers. And you can show that h1, h2, all of these are 0 for this case, because you can't even construct the complexes first. So that's one way to do it, and it's a very simple example. Let us now take a look at another example, and that will hopefully make things even more clear. So take this example. We have a simplicial complex. This is example 2, and we have a complex or simplicial complex as follows: p0, p1, p2. Then I have p0, p1, p1, p2, p2, p3, like this. And at first we will try to compute the zeroth homology group. So let me break it down like this: computation of h0 of k. So from this set of complex, we can easily see that any element, let's say c, that belongs to c0 of k can be written as c equals to a p0 plus b p1 plus c p2. Okay, so let's use this as c prime so that we don't confuse two c's, where a, b, c prime belongs to the set of integers. And this is nothing but a group of z with direct sum of z, with direct sum of z. What does this direct sum means? It just means that we have three z's over here that are related to each other by a direct sum. This just means 3 copies of z. That means to represent this element c, you need 3 copies of z. That's what it means, because you can regard this a, b, and c, all the c prime, all these guys as some bases, and they belong to z. So you need 3 copies of them. Okay. Now to find z0 of k, we do the following. That is, we take the boundary of any element c that is belonging to your c0 or the chain thing, and from here these elements look like there's a linear combination of the zero simplexes. So now if I do that, then what I have is a del 0 p0 p, but these are what? This p0, p1, p2, they're all points, right? And the boundary operator is acting on them, so this is just 0. So therefore we conclude that our z0 is actually equal to our c0. Okay, because what is a Z0, right? These are just my group or set, whatever you want to call them. It's actually a group, but if you also consider them as a set, that's fine as well. The Z0s are just the set of 0 cycles, right? And what was a cycle? A cycle was something, you know, that belongs to C, but when you apply a boundary operator on them, they give you a 0, right? And here we can see that for any element that belongs to my 0 chain group or 0 chain set, if I take any element from this 0 chain set and apply the boundary operation, that will give me a 0. So all the elements that are in my chain group are also in the Z0 group, okay, or the cycle group. So that's why I write it like that. Now that we have done, we have found out our Z0, now we need to find out the boundary sets or the boundary group. So now to find the boundary, B0k, we do the following. And recall, what is a boundary? This boundary, recall, it will be, okay, let me write it again. B0k will be the set of all chains that will satisfy let's say this is some B that belongs to like B0 of k, then this will be 1, and here you'll have some D which is an element from the 1 chains, okay. I mean, sorry, not 1 chains, rather 1 simplex, not 1 chains, my mistake, 1 simplex. So now we have L1 acting on this, let's say D P0 P1 E P1 P2 F P2 P0, and this D E F, they also belongs to Z, because any element on a 1 chain group can be written like this, okay. So that's why I have to take any element that belongs to a 1 chain, okay, and then I have to take it and I have to operate the boundary operator on it. So now let's use our previous knowledge of the boundary operator, what it does, and if I do that, we'll get D P1 minus P0 plus E P2 minus P1 plus F P0 minus P2. So you have, ultimately, if you simplify this thing, you get F minus D P0 D minus E P1 E minus F P2. Let's call F minus D as some D prime P0, D minus E as some E prime P1, and E minus F some F prime P2. I'm just using a simpler notation where D prime, E prime, and F prime also belongs to Z. And this is very easy to see. You have 2 integers, you add them or subtract them, you get another integer, right? And this result or this thing is just the image of my boundary operator, right? relevant in this case. So if you have any element c, small c, that belongs to the 0 chain, that we wrote down earlier, we see that any element, so these are the elements of your, first let me write down this, these are the elements on your boundary sets, set p0 of k, right? But doesn't this look a little bit familiar, this one? Yes, it looks familiar. Why? Because just look at this, c0 of k, right? It's the same thing, even though I used D, E, F, but all of this A, B, C prime or D, E, F, all of them belongs to Z, and these are just linear combinations of what? Our zero simplexes. So these are the elements on your boundary set, right? But if they are the elements of the boundary set, this guy is over here, then they have to satisfy D plus E plus F prime equals to 0. Why is that? This is coming from the fact that the boundary of a boundary is 0. So if I apply the boundary operator on this element, it will be 0. And if you use this boundary operator on these elements like this, you will easily see that since these are zero simplexes, they are by definition 0, right? So now what we have is that since our constraint is something like this, we can write it as f prime is equals to minus d prime plus e prime, like this, and put this back into this equation. If we put that back into the equation, then any arbitrary element of p0k can be written as d prime p0 e prime p1 minus d prime plus e prime p2. And now we want to compute, because we have all the tools, we want to compute our zeroth homology group, that is given by this. But you will realize immediately that this is not a straightforward procedure, right? Because so far we don't have anything useful that will actually help us in computing the zeroth homology group using this formula or this prescription. So this is where we will use the fundamental theorem of homomorphism. So let's call this one. We see that one is not a straightforward way to compute it. Compute h0 of k. So we will rather use the fundamental theorem of homomorphism to compute it. To use the fundamental theorem of homomorphism, at first let us define a homomorphism if a homomorphism such that it maps z0 of k to the set of integers as follows. And the reason this type of homomorphism was chosen is that from the equation that we saw earlier that was putting a constraint, that is this guy over here, this equation puts a constraint, that is d prime plus e prime plus f prime is equals to 0. But if you notice carefully, this 0 is just the additive identity on the group Z, right? On the set of integers. So the kernel of f will be something that will act on the first group, that means our Z0. You know, we want to find out the kernel when we are using this fundamental theorem of homomorphism, right? We want to have such a homomorphism that will take our elements from this group. So this is a group, and let's call that G1, and this is another group, right? So if I choose this type of homomorphism and I have a constraint where any three elements were added together on Z gives us the identity, I can easily compute the kernel. So this is why we chose a homomorphism like this, okay, just so that we can use the fundamental theorem of homomorphism. So with that and the constraint equation, with that and the constraint equation, we get a plus b plus c equals to 0, which tells us again that c is equals to just minus a plus b. But recall that the fundamental theorem of homomorphism told us that this is just our Z0 of k by the kernel of f was isomorphic to the image of f, right? So we have such f that satisfies this thing. We have the kernel, the identity, and Z0 was what? Was also a group. And what is the image? The image is easily seen from the definition of this homomorphism. The image belongs to the group of integers, right? So essentially you can easily write a0 of k is isomorphic to the set of integers. This is how we use the fundamental theorem of homomorphism into computing homology groups. Alright? And now we want to compute the first homology group. So